Yeah, it's okay.
Yeah. Okay. So, good evening, good morning from Spain, good evening in Australia. Today I'm going to present a talk about Markov chains applied to Pareto paradox, and I will concentrate the talk about a specific problem of coin tossing about coin tossing. This talk is from a work with Camilla Megnin from French. He will stay here in Spain with me some years ago, the last year, and we deal with this problem. How the problem is how to wrong or how to lose in games can make a right, can make a winning game. So let me show you the contents of the presentation. I will explain the Pareto paradox. I will introduce Markov chains, some specific definitions to use the specific problem about coin game, and applications on the conclusion. See the time. Introduction, the Pareto paradox, it's easy to define. It's just to say that there exist two losing games. For instance, you have two losing games, and then you make some combinations with these two losing games, and then you obtain a winning game. So how from two losing games you can obtain a winning game? It's the goal of this work. So sometimes, first of all, maybe it's hard to think about that, but if we think in some flipping games, so you can imagine that it's possible. Imagine the situation. You have a game when you lose one coin every time that you play. You don't work the play. Every time you play, you have you lose one coin. So it's normal to think that this game is a losing game. Let me show another game. The game now called Game B. You can how much money you have left. 10 euros, 10 coins, 90, whatever. And if the number of coins that you have is even, then you win 3 coins. And if the number of coins that you have is not even, then you lose 5 coins. You can think that, again, this game is a losing game. Sometimes you win 3 coins, but sometimes you lose 5 coins. So both game A and game B are losing. What happens if I mixed B and A, B and A, B and A, B and A? So it's a winning game. Imagine that you start with 100 coins. What have to do? So you play with game B, and then you get 3 coins. You play with game A, you lose 1 coin. Again, so when you play with B plus A, at the end you win 2 coins from 100, 102. When you play again with B and A, you again win 2 coins, and so on. So when you mix A and B, in this case BA, 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 you obtain a winning collision. Let me show you the specific problem that I want to concentrate in this talk. Show you a little more complicated game. Think that you have game A, where you have a coin where the probability of landing head is 1/2 minus alpha. Alpha is a small value. So you can think that with this game, the probability of landing head is less than 1/2. So if you flip a lot of times this coin, you lose money, instead of that the head is equal to win 1 coin and tail is equal to lose 1 coin. So when you flip a lot of times this money, this coin, the things are bad. Think another game. Game B. Coin 1, you have in game B 2 coins. Coin 1 lands head with a small probability, 0.1 minus alpha. My alpha is between 0 and 0.1. It's a positive probability. So it's not used to obtain head. It's not used to win 1 coin. So clearly, when you flip, you choose the coin 1, you lose money. Always it will be tile at most, with high probability, and then you will lose coins. What happens with coin 2? Lands coin 2, with coin 2, lands head, it's the probability, the lands to head is with probability 0.75 minus alpha. In this case, it's more useful to win. But anyway, suppose that the game is the following. If the current game is multiple of m, we toss flip coin 1. Otherwise, we flip coin 2. In this situation, when m is equal to 3, for instance, you lose money, because most of the times you will toss coin 1. Suppose that I have that m is equal to 3. So when m is equal to 1 or 2, you toss coin 1. So most of the time you will toss coin 1 and you will lose. We have done some simulations with this game, and we have obtained the following. Game A is clearly losing game. Game B is clearly losing game. What happens when I combine A and B? Sometimes, even randomly, we get a winning game. Okay. Let me show just some examples. We have done this example simulating with a program called R. We have done some manipulations, some computations, and we will simulate this with different combinations, playing 50,000 times, 15,000 rounds. We have considered that alpha is equal to 0.005 and m is equal to 3. What happens? No. Okay. So when I consider here, let me see here. When I consider just game A with 50,000 simulations, I lose money. With 50,000 simulations, we obtain minus 600 coins. What happens with B? When I consider B, after 50,000 simulations rounds, we obtain that we lose about 350 coins. What happens when I mix A, B, A, B, A, B? It's again a losing game. Losing game, it's quite similar to the previous one. A, B, A, B, A, B. But what happens when I play with A, A, B, A, A, B, A, A, B, A, A, B, and so on? So in this case, I got a winning game. What happens when I have BBA, BBA, BBA? I'm a losing. It's a losing game. So for our simulation, sometimes at the beginning, it looks that we win, but when we make this simulation around 5,000 rounds, we lose money. What happens when I apply ABB, 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 ABB? I win. And what happens when I make a random playing? AB with, I choose AB in a random way. So when I make some random combinations with A and B, I'm winning. And finally, what happens when I know the best option? I win. I choose A or B, depending on the situation. If the number of coins is equal to m plus 1, or a multiple number of m, a multiple number of m plus 1, or a multiple number of m plus 2. Let me show all the examples. In these cases, here I have some winning collisions, some winning combinations, AB and random, AAB are winning, and here knowing what happens before, what happens, choosing A and B and make convenience, I also have a winning game. And when I choose ABB, 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 let me show more precisely the benefits. When I take off this line, the benefit when I know the previous profit, it's the best way to play. Or if I take off, if you meet this situation, I have this draw here. Okay, so what I see here is the best situation is this line, this pink line. When I play with ABB, 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 and so on. Okay, so I want to analyze with Markov chains this situation. How to analyze where I'm going to, which alpha I have to take in this game. Let me show, please. In this game, which alpha I have to consider in order to have a good combination to win. So first of all, to use the Markov chains, I have to introduce Markov chains. What's a Markov chains? Markov chains is a chain, a combination, applied that you make rounds and rounds and rounds and go on, that has one condition. Here, this condition. The conditional probability distribution of future states of the process depends only upon the present state. It means what happens from now on in the next state. It depends not from all the previous states. It just depends from the present stage. It's the unique condition that Markov chains considers. So let me introduce just some notations. I don't want to go through in this talk about the Markov chains. Just I want to give you some ideas. You can go in depth in the paper. Initial probability distribution is called Q. Q. You will see that I will just put Q. Transition probability, what happens from now to the next step, is from a matrix where you have, we will consider that this matrix is P, and for each line you have the situation from now to tomorrow. I will show you an example. It's what happens when, for instance, in this matrix, I have the situation from now to tomorrow, from now to tomorrow. Okay, I think just that, just these two simple situations. Q is the initial probability distribution, and the P is the transition probability, where for each row and column says what happens from now to tomorrow. Let me show here an example, customer of a bookstore. Here I have an example. Think that, for instance, each day a customer of a bookstore can do 3 different actions. Customer can not go into the bookstore, and the other 2 possibilities are go to this bookstore and buy. And doesn't buy a book or go into store and buy at least one book. Don't go and not buy, go and don't buy, and here, go and buy. These three situations. So in this case, think that the first day the customer has a probability of 1/2 to visit the book store without buying. It means 1/2 here, this situation, and a probability of 1/2 of buying at least one book, 1/2 here. Which is the initial probability distribution? So I have here 0, 1/2, 1/2. Let me show here. 0. It's not possible that the first day the customer doesn't go to the bookstore, and 1/2 go and doesn't buy, and 1/2 then go and buy. What happens the first day? Let me specify what happens here. Here, the same test that it was before is here again. Suppose that when the customer doesn't go into the bookstore, the probability that the next day still not go to the bookstore is 25%. This quantity here. This quantity I put here in the transition matrix, 0.25. This value is here. And the value, the probability to go without buying is 1/2. Here, this number, 1/2, 1/2, 1/2. And the probability to go and buy is 25% here. Is the situation. If I go, the next day, the probability that of my actuation it has these values here. Okay. What happens if I visit the bookstore, but not buy a book, any book? The situation is, think that I have 1/2 to visit the bookstore without buying here, to go and buy here. Okay, so when I go and don't buy, the next day I will go. Maybe I will buy or maybe not. The same probability. Here is the transition matrix. What happens when I buy at least one book? The probability is 53 here, 53%, and 54% here. So it's the transition matrix. You can see that rows are the present day, and the day what happens tomorrow, here the columns. Columns are this. What happens tomorrow? What's the probability to that I will not go to the bookstore? If I have done this, the probability is 25%. If I have gone this, the probability is 0. If I have done this, the probability is 33%. Okay, you can see that the rows are equal to 1, but the columns are not equal to 1. Anyway, so if I have a problem like that, I can define the initial probability distribution and, the transition matrix. I also can define this game with a graph. I have the initial probability distribution, and here I have the graph of the corresponding situation. I don't go through this. You just think that you can define the probability matrix here are a specific graph. Anyway, what's the Markov change? What's the main theorems of Markov change? Theorem 1 says that if P is the transition probability, then ij entry of this probability, when I power P to n sometimes, give the probability of the state Sj after n steps. So imagine that I have the probability, the matrix, the transition matrix and I make power n. So when I obtain P power n is the matrix, what happens after n rounds. Here you can see that what happens in the after n rounds. Here is the situation. I just have to multiply the initial situation to product P power n, and I get what happens after n steps. In our case, I have the initial situation is this one, in our case of customer of bookstore, and here I multiply with the transition matrix, and is the situation after the first step. What happens if I have a regular Markov chain? What's a regular Markov chain? It's a situation where the transition matrix has only positive elements. It happens when I have a transition matrix, I just have to make P power P, and if all the elements are positive, the matrix is regular. In this situation, the matrix is regular, and I have to apply the fundamental limit theorem for regular chains. In the paper, this is the demonstration about this theorem. I don't want to go in depth about it, but you can check the proof of this theorem, the paper. So what says then when I have P power n in the limit situation, at the end I have a specific matrix. Just imagine that. So this theorem, fundamental limit theorem, studies what happens in the limit situation when I have made a lot of rounds in my game, in my customer's player or whatever. Okay, so the Markov chain says that when I have a transition matrix and I multiply this a lot of times, I get a specific matrix, which is the last situation, the stability situation after a lot of rounds. Here, the equilibrium vector that I also have proof in the paper, the equilibrium vector says that if I have a probability matrix, distribution matrix, transition matrix, I just have to find this value, this vector, in order to tie the stability situation. Let me show just an example for this situation. This theorem, theorem 4, says that if I have the transition distribution here, I just have to obtain V, this value here, V, in order to obtain the final distribution. In our case, I have this matrix, I want to solve this situation, and the equilibrium vector, what happens at the end, it will be the same probability to don't go to the bookstore, go to the bookstore without buy any book, or go to the bookstore buying one book or buying books. The same probability in this example. So go back to the first example. Let me show you a mathematical study of coin game. In this example that I have shown you before, in the flipping coin example, you have a game A and game B. Game A with probability of landing had the same than before. I have the same situation than before. So I want to study this situation with Markov chain. It's not easy. Let me show some specific things. Here, you can make some experiments. We have done with her. You can count how many combinations can you obtain to get after 6 rounds to get 6 coins, and how many combinations are possible to get 5 coins after 6 rounds, and so on. So what we have done is to study what happens when I have done 6 rounds. In this case, after 6 rounds, I have lose money. The expectation is to lose a lot of money. It's less than 1.5. What happens with the game? with A. What happens with game B after 6 rounds? We have analyzed what happens. I don't go to, it's not the goal of this talk to go in depth about what to do, but just imagine here are all the combinations to get 5 coins, 6 coins, 5 coins, 4, 3, 2, 1, 0, and so on. I mean, excuse me, 6 heads, 5 heads, 4, and so on. The gain in these cases are 6, 4, 2, 0, -2, -4, -6. If I count all the situations, I lose money. It's less than one half. What happens if I combine A, B in random situation? When I do that in random situation, I have that the benefits is more than one half. So I will win when I combine A, B in a random situation. So what I'm going to study with Markov chains is what happens with A, what happens with B, and what happens when I play with A and B in a random situation. Is the sketch of what happens with A, B, and B after 6 rounds. What happens after n rounds when n tends to infinity? Oof. Let me define the Markov chain. Here, it's the transition distribution matrix. Here, what happens when the current gain is multiple of 3 and the next time the current gain is multiple to 3? The situation is impossible when it's equal to 0. What happens when the current gain is equal to 0 and in the next time it's equal to 1? The probability is that I win, and so on. Here, for player A, I study what happens in each situation. Okay? So you can go in deep, but just you need to think when I have here the gain is equal to 0 module 3, what happens? What has to do in order that the next time the gain will be equal to 0, equal to 1, equal to 2 module 3? What happens when the gain is 1 module to 3, and in the next time the gain is 0 equal to module 3, 1, or 2? It's the situation. So if you have this situation, you can, when you apply alpha equal to 0.005, you have this situation here, this matrix. This matrix is regular, and then you can obtain what happens at the end after a long ways. So in this situation, I have the probability is 1, 3, 1, 3, and 1, 3 to win, to be stay in situation that you have the gain equal to 0 module 3 here, to win in the situation that the gain is 1 module 3, and here the win to be in the situation that the gain is equal to 2 module 3. So in this situation you lose. What happens with game B? I study again the same situation, which happens with the current gain is equal to 0, and in the next time the gain is equal to 1, and so on. I analyze all the cases, and I obtain this matrix, these values, and this matrix is a regular matrix, and happens that in this situation, the first probability is this number, the second, and the third one. It's the gain where the number here is that the gain is 0 module 3, the gain is 1 module 3, the gain is 2 module 3, and it's losing because it's less than 1/2. What happens when I combine A and B in random? 1/2 of the first transition matrix, 1/2 of the first transition matrix. Here in this case, I have that this matrix is again regular matrix, and in this situation, I obtain more than 1/2 benefits. When I go to the end, I have the benefits. So what I have done is, what happens with alpha in the game A? Can I modify alpha in game A in order to win? The answer is not. When I consider this matrix here, this matrix, let me show here, here, with alpha, I got this matrix, and 0.5 minus alpha never will be more than 1/2. Never, 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 if alpha is positive. So always I will lose. What happens with B? Again, I put here alpha. I have this situation when I solve the problem, when I compute V with alpha, with these values, when alpha will be more than 1/2. So we have studied, we have discomposed these values, we studied that this never will be more than 1/2. Never, 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 never. It has no solution. And what happens when I combine A and B at random? The situation is, I have this equation. When this value is more than 1/2, you make some computational studies, and then you get that it's winning when alpha is less than 0.01. So if alpha is less than this value, when I mix A and B at random, I will win. For instance, if alpha is equal to 0.005. Okay. So applications about random Parrondo paradox are a lot. For instance, you can see an ecologic. Give me just 1 minute, not more. In ecology, it's studied that nomad human situation, it's a losing situation, and the colonist situation are two strategies that always are losing. You can survive if you just are nomad or just a colonist. So you need to mix both. It has been studied that may suggest border applications in Homo sapiens, and what we do? We need to accommodate about what happens. A lot of people it's nomad, and a lot of people it's colonist. To mix these situations. In finance, it's trivial. It's not possible to buy all the times or to sell all the times. You need to mix, and you need to mix some strategies. If there is some economist here, I'm sure that she will know more than me. Here you have some strategies to mix, to take care about your money, and to mix all the strategies. So sometimes you lose, but if you mix some strategies, you will win. In reliability theory, also, you can obtain benefits or not, and also in biology. Biology, maybe you have a medicine that goes wrong and another medicine goes wrong. When you mix, you get a good medicine. Really, this Parrondo paradox is used in some situations here in oncology and in biological sensors. It's used. It's really used nowadays. So, in conclusion, I want just to present that maybe sometimes lose plus lose is equal to win. What happens with the flipping coin problem that I have presented here, and with some situations that I have also presented here. So I just want to mention one thing. Thank you very much for your attention. I hope that you has enjoyed a little, and you think about that. There are some situations that when you mix, you win. Thank you very much. That's all.